we have to look a little bit more specifically at the particle level. What is happening when a solvent is dissolving a solute? So water, which is our main focus, so water, that is our solvent. And we know it's present because we see AQ. Specifically, we need to know what happens when water, our solvent, dissolves a salt, which we also know as ionic in chemistry class, acids or bases. So what happens is that when you dump a salt, an acid, or base into water, the water, it actually will yank the cation in that salt, acid, or base away from the anion. So it separates the ions. So the ions go from being held in fixed positions in their crystal lattice to being able to swim freely. So they're swimming in the solution. And these solutions, because of these freely swimming or moving ions, these solutions conduct electricity because they have moving or mobile ions. So electricity is the result of moving charges. So let's take a look here. So we have an ionic compound. This is a salt. So this is a salt, or what we refer to as ionic, and we recognize it because there's a metal bonded to a nonmetal. In salts, their typical normal phase is solid. So this would be like in the salt shaker. When we take this and we dump it into water and stir it around, water yanks the Na cation away from the bromide anion. So what we end up having in solution is the Na, the sodium cation, carries a +1 charge, and now its phase is aqueous, meaning it's spread out, dissolved in the water, swimming freely and separated from the bromide anion. So quick little notes here. So here, this is the crystal lattice. Where all of those ions, sodium and bromide ions, they are held in those fixed positions, making that geometric crystal. Now we dump it in water, and now we have swimming ions. So we have swimming ions in solution. And it is this side, the right-hand side of the equation, that when this is formed and present in our container, this is what conducts the electricity, has a current, able to carry a current. So let's take a look at the next example, magnesium chloride. It is also a salt or ionic compound, metal bonded to a nonmetal. Magnesium being first in the formula is your cation. Water yanks magnesiums away from the lattice. So now we have a magnesium. It's set free, so we put it as aqueous. It's a cation, so it uses a plus charge. But magnesium is in group 2, so it actually carries a +2 charge, not a +1. When the magnesium's ripped away, some of the chlorides, chloride being second in the formula, it functions as the anion, and it uses a negative charge. Chlorides are in group 17. They're one move away from their noble gas, so they use a -1 charge. But notice in the chemical formula, for every one magnesium, there are 2 chlorides. And when you add up their +1 and their -1 and -1, charge is 0. So on the right-hand side, we have to have a charge of 0. So right now, if we leave it as magnesium ion, +2 charge, plus a single chloride ion, -1 charge, now we don't have a balance of charges. So we have to remedy this. For every one magnesium cation that's pulled away from the lattice into solution, 2 chlorides are also pulled away. Okay, so now I'm moving down to the next one. Now this is definitely not a salt, okay? This is a molecule. So this is an example of a molecule. And we know that because every element present is a nonmetal. But we're going to get more specific as our formula starts with hydrogen, and the hydrogen is bonded to other nonmetals. For us, when we see this sequence, we're going to learn to recognize that as an acid, and these are on our table K in our chemistry reference tables. So hydrogen's listed first, so it functions as the cation, and the SO4 is the anion. So water comes along and it rips a cation away from the molecule. So now we have a hydrogen ion that's freely swimming in solution, and we know that because it's showing its charge and it's aqueous. And when it's pulled away from this polyatomic ion we know as sulfate. And when you look up sulfate, it carries a -2 charge, and we know that it's been pulled away from the molecule and swimming freely because it's aqueous. But if we look at those charges, they don't balance out to 0. They don't cancel out. And when you look at the formula, it requires 2 hydrogens to every 1 sulfur. So like the magnesium chloride, we're going to put a 2 out in front of the H+ ion. Last example here is LiOH, and this fits into our category of ionic or a salt because we have a metal and a nonmetal. However, this is a prime example of a substance that we will find on table L, okay, where we have a metal bonded to a hydroxide. So when we have a metal bonded specifically to hydroxide, we're going to recognize those as an example of a base. But like all the others, when we take this material and we dump it into water, water yanks the cation, Li, away from the anion. So the Li, group 1, +1 charge, and we know it's yanked away and swimming freely because of the phase AQ. And for each Li that is stripped away from the crystal lattice, we end up with also a hydroxide, table E structure. It carries a -1 charge, and it is aqueous. So you'll need to be able to write out these equations, these dissolving processes.